Let's try out some problems from lesson 9-4 on common logarithms. Um, so I'm going to work through 4 problems with you in the hopes that this will give you a good, not just a glimpse, but like a really good in-depth sense of how we're going to problem solve and how we're going to work in both log properties as well as the common log into problem solving. This problem, actually, I did this in the previous video, but I thought it was worth revisiting so that I could extend it a little bit. You'll see this in the textbook as well, right? Log base 6 of 8 in terms of common logarithms. You're being asked to express this question differently. So what power of 6 produces 8? I don't know. It's not 1. 6 to the first is 6. 6 to the second is 36. It's somewhere between 1 and 2. But the point is that I want to write this not as log base 6, but log base 10, because that's the common logarithm. It's what's more readily available on the average calculator. So I write that log base 6 of 8 is equal to some unknown value. I then rewrite it as an exponential equation. This outcome of 8 is equal to the base of 6 raised to the x. I find the common logarithm of both sides, and then I start using my logarithmic properties such that log base 10 of 6 is a power being raised to another power, which turns into multiplication. Just here's a quick reminder. I don't know if you need it, but it's just, if you had 2 to the third to the fifth, this would turn into 2 to the 3 times 5. You're multiplying 3 times 5. And so remember, logarithmic properties come from exponential properties. So when a power is raised to a power, you end up multiplying. Uh, if we want to isolate this x, we divide both sides by log base 10 of 6. Just another quick reminder also that you don't actually have to write this base of 10. It's perfectly sufficient to write log of 6. I choose to write that base of 10 because I think it really kind of reminds us of that common log. And so look, x is all alone. It's equal to the ratio of log of 8 divided by log of 6. This is the same as log base 6 of 8. So I have successfully written log base 6 of 8 in terms of common logarithms. This is the same thing as log base 6 of 8. I mentioned this in the previous video, but I don't think I did a problem like it. What if I had the same exact question, but instead of being asked to write it in terms of the common log, I was asked to write it in terms of log base 7? So can I convert log base 6 to log base 7? And the answer is the process is identical. I mean, if you just take a look at the algebra here, of course, you can pause this video if you choose, but the algebra is identical, and so you end up with, I can write log base 6 of 8 as log base 7 of 8 divided by log base 7 of 6. That's that change of base formula. So my argument is that finding log base 6 of 8 is the same as finding this ratio, and here's some calculator proof kind of supporting that point. Let me just see if I can block out some of this light here. So uh, the first line is log base 6 of 8. You get 1.16 approximately. And the next line, you've got log base 7 of 8 divided by log base 7 of 6. And you end up with the same exact outcome. So hopefully that's some proof of what it is I'm trying to say, that we can convert a particular base, to any other base of our choosing. Let's get into something that's a little bit more sophisticated here. How about a logarithmic, or the use of logarithms to solve an equation that was previously kind of just impossible for us to deal with? When this problem comes into focus, you'll see what I mean. I plucked this problem from the textbook, and my letter T is illegible, so I replaced it with the letter X. But the equation is 7 to the x minus 2 is equal to 5 dx. And this is your kind of worst nightmare come true, because the bases aren't the same. There's no way to easily manipulate those bases so that they're the same. And now is when the logarithm really makes its power known. You'll notice that I'm finding the common logarithm of both sides of this equation. It will take these exponents and essentially drop them down into factors. I'm just using the power property, or the power of powers property. So once I have that x minus 2 is being multiplied by log of 7, and that equals x times log of 5, now I've got to go about isolating these x's somehow. So I've decided to use the distributive property, and I've shared this x minus 2 with this expression, and that's how I've got this outcome here. I didn't do anything on the right side. Now I'm kind of collecting terms. So this is a pure number here. Think about this. Some power of 10 is equal to 7 times 2. So this is a pure number but this is an algebraic expression. So I want to bring this x term over here and bring this numerical term here. So I'm adding 2 log 7 to both sides. And then the next step, I'm subtracting x log 10, x log 5 from both sides. So what you'll see is that I've collected the two x terms on one side of the equation. This is a pure number. What do both of these expressions have in common? They both have an x in common. So I factor out the x, leaving me with this horrible looking expression here is just a pure number. So how do I isolate the x? I divide by this pure number. You notice I wrote it in green here, but when I go to my calculator, what I'm going to ask it to do is this. And I tend to like to use parentheses. I'll kind of have this wrapped up in parentheses, 2 log of 7 divided by log of 7 minus log of 5, and you will get that outcome of 11.5665. Let me turn this light off here so that we can get a better image. And I'd actually like to use the calculator to show you that that outcome is valid, and then I'll use Desmos to kind of seal the deal. But here we are. Let's do in parentheses 2 and the logarithm of 7, and we want to divide that by, and this gets fuzzy if I don't kind of zoom in on it frequently. Cool. And I want to divide that by the logarithm of 7 minus the logarithm of 10, or excuse me, of 5. And I'm being kind of diligent about my parentheses, and here's that answer I showed you on the paper of 11.5665. And the more decimal or the more significant digits you report, the better off you are, the more accuracy you're going to get. Uh, I've had students tell me in the past, like, I don't even need these logarithms. I could have just graphed this on a graphing calculator and looked to see where this exponential curve intersects with with this exponential curve. And I'd like to show you why that's a tough proposition here. If you look at what this looks like on Desmos, and remember Desmos is a lot easier to manipulate than your calculator, the two curves are kind of shooting upwards, but it's barely discernible that they're getting closer. Here I am way up at y values of 100, and the lines maybe look like they're kind of getting, the curves getting closer together, but how long am I going to have to do this for? Even if you go to the table settings and decide that you're going to have your outputs start at, let's say, 1,000, way up at 1,000, and all the way up to 1,200, they're still barely closer to one another. So think about what happened here. I mean, they ended up intersecting at around 11.56. You're taking 5 and raising it to the 11th power. You're getting an output on the order of magnitude of 100 million here. So remember, 10 to the 6th is a million, 10 to the 7th is 10 million. Your output is at 100 million before these two curves. As I kind of scroll out, you can see it before the red and the blue intersect. So the algebraic method of solving it is a lot more accessible and a lot more accurate than trying to graph this. Let's look at one more example, this time in inequality. And the good news is that with these inequalities, if the inequality is exponential, I'm not worried about any domain restriction. So let's see if we can get this to behave and to cooperate. Here's the original inequality. And again, I'm not concerned with any domain restrictions. You'll notice that I'm finding the common logarithm of both sides in order to gain access to these variables that are stuck in the exponents. You've seen this happen a number of times now. This power drops down and becomes a factor on both sides. Not much happening here on the left side other than I'm removing this dot notation and just it's understood that this is the product of this logarithmic expression in 2x. And here I'm using the distributive property once more to kind of share out that x plus 1. And then here's where the creativity kicks in. You collect these x terms on one side of the inequality, leaving yourself with just a pure number here. These both have an x in common, so we're going to factor that out. And if I want to isolate this x, I need to get rid of this kind of horrible looking coefficient. So I divide both sides by 2 log 3 minus log of 6. And again, you've got to have some calculator proficiency to to get it to take this expression and simplify it. But you find that as long as x is greater than or equal to around 4.4190, then this original inequality will be true. When is this inequality true? Well, whenever x is greater than or equal to 4.4190. So I hope that was helpful in terms of seeing how to solve um, problems using the common logarithm.